Hello, my name is Tom Overby. I'm a professor at University of Illinois specializing in the area of electrical power systems. In this slide set and the next two, I'm going to provide an introduction to power system transient stability analysis. Transient stability is a power system analysis application that considers the response of the power system to disturbances on the time frame of seconds. So it's a problem that's formulated as a set of differential and algebraic equations where the differential equations have a time step of perhaps a quarter or a half cycle on the order of about 1/200th of a second. The algebraic equations then represent the network power balance equations. And usually transient stability is run for several seconds up to perhaps a minute or two. In going through these slides, the assumption is that people have a basic understanding of power system modeling, and this includes understanding, at least to some extent, the power flow. To put the transient stability problem in context, it's helpful to look at various power system timescales. This slide shows an image that came from the book by two of my colleagues, Professors Sauer and Pai at University of Illinois, in which they break down the power system problems from very fast timescale problems such as lightning propagation, where you're looking at time on the order of microseconds, all the way out to the longer term, what we call quasi-steady state, which is a power flow application, where you're considering the response of the power system as it changes quite slowly with time constants on the order of more than several seconds, perhaps a minute or longer. In the power flow, for example, we assume that the power output of the generator stays reasonably constant, and the loads can be usually represented as constant power loads. Transient stability then fits in the middle of this time scale with, again, a time frame that might range from cycles out to perhaps minutes. Now, this is in contrast to the power flow, which is the first application that most people encounter for power system modeling. Power flow looks at the quasi-steady state operating condition. So here, what we can do is we can represent our power system as a set of algebraic equations. In this slide, I've represented them as a vector G with the variables Y equal to 0, where these variables include the bus voltage magnitude and angle at most of the buses in the system. Sometimes when we're modeling a generator bus, we'll assume that the voltage magnitude at the generator is fixed. So in that case, we neglect that equation for the generator, and we just have a single equation saying that the real power output of the generator has to be equal to some specified value. Okay, so these models represent the longer steady state, where we represent our generators relatively simply, as I said, as PV buses. So we're assuming there's some sort of control system on the generator that holds the terminal voltage of the device constant at some specified value, and its real power constant at some specified value. And then devices such as LTCs, the load tap changing transformers, are assumed to respond so quickly that they become algebraic. That is, the LTC is trying to hold the voltage at its controlled bus at some specified value, and usually we assume that we've got constant power loads. Okay, in contrast, transient stability looks at the dynamic response of the power system, where usually what happens is the transient stability problem is set up at some initial operating condition, and then we use a set of differential equations to represent how the system variables change with time. So we're going to say x dot here is equal to f of xy, where y are usually related to the variables from the power flow. That is, y is often the power system bus voltage magnitude and angle. X is a set of dynamic variables, which we'll introduce in just a second. So we're solving x dot equals f of x at the same time that we're enforcing a set of power balance equations that represent the fact that our generators are connected to usually an AC transmission system. So we start at some steady state point. Usually the steady state point is provided by the power flow, and then hopefully following some sort of disturbance we return to some new steady state operating state. The idea here is the models represent the transient stability time frame, that is with dynamics ranging from cycles up to perhaps several seconds. So in transient stability, it's very common to assume that the load tap changing transformers maintain a constant tap position throughout the study, whereas the voltage on the generator terminal is allowed to vary. Okay, what are some of the typical questions we might address in the transient stability? Well, one which is solved quite often is to determine whether the generators will maintain synchronism following a fault. And this graphic here on the right side, I show over the course of, in this case it's about 4 seconds, how the generator internal angles change following a fault on the system. So here we've got a steady state condition, and then at time t equals 1 we apply a fault, and then we get some sort of response, and we're hoping that the generators stay in sync with one another, which they do in this case. And a separate type of study that's done with transient stability is to determine whether the system voltages and frequencies will stay within some acceptable limits following some large disturbance, such as a loss of a generator. So this is shown in the second graphic over here on the right, in which here I'm showing the response of the power system over the course of 20 seconds. Here what I'm doing is I'm plotting the bus frequency at the generators at different locations in the system. This is actually from a relatively large system that's modeled with about a 17,000 bus model. Here I'm showing a few selected frequency values. The disturbance occurs at time t equals 2 seconds. Large amount of generation is lost. That causes the frequency to decay. And then what we're wondering in the transient stability problem is whether that frequency will stay within specified limits. In this case, it goes down to about 59.72 hertz at the lowest. So that would be an acceptable response for this system. A third application for transient stability studies is to look and see whether we can start large motors. As you might know from a course in motors, when an induction motor is started up, it consumes a lot of reactive power. That tends to pull the voltage down. And you might use a transient stability study to determine whether the voltage maintains acceptable values in order to actually start up your large induction motor. Okay, so this next slide shows in kind of a graphic form the various power system components. Starting here in the middle on the right is the power system network. The purpose of the network is to take the electricity from the generator and supply it to the loads. And this is usually what is represented in the power flow. You've got the network, the generators are modeled as constant real sources at some specified voltage. The loads are then represented by a constant P and Q characteristics. In transient stability, sometimes on the load side we'll take and come up with more detailed load models, while on the generator side what we'll often do is represent the response of the machine in much more depth. The generator itself is going to be represented as an electric machine, which models the synchronous machine there. The output of that machine will be controlled by a device called the exciter, which maintains voltage control. The mechanical power into the governor or into the generator is supplied through a furnace and boiler into a turbine, which is controlled by a device called the governor. And then sometimes we'll have a stabilizer on the system whose purpose is to help stabilize the response of the machines following some large system disturbance. So it does that by sending an auxiliary input into the exciter. So what we'll do over the course of these slides is to at least give a brief introduction to these various types of models here and see how they're put together to come up with a dynamic study of the power system. Okay, the starting point for this is to expand on the electrical model for the generator. In the power flow, the generator is modeled as I said, a constant power source with a fixed terminal voltage. So in the power flow, VT is assumed to be constant. In transient stability, we use typically much more detailed models to represent the dynamics of the response of the electrical machine, the synchronous machine that sits behind the voltage terminals here. Now initially what we'll do is we'll introduce the problem through what's known as the classical model, which is really about the simplest dynamic model for a generator. The idea in the classical model is we assume that the internal voltage of the generator is at some fixed voltage magnitude, and then there's an angle associated with it where the angle is going to change with time, and this voltage source sits behind the transient reactance here, represented as an impedance J XD prime. Then the power output from the generator, P sub E, is determined by noting that if we've got a lossless impedance here, which we do because this is just a reactance, we can represent the power transfer through that impedance just as the magnitude of the two voltage sources across it, the terminal voltage and the internal voltage, divided by the reactance times the sine of the angle shift between the internal angle and the terminal. Here what I've done is I've set the terminal angle to be 0, and then we introduce an internal angle known as the generator delta to represent its internal characteristic. I should note that EA is also sometimes referred to as E prime, just represents the internal voltage of the generator. Okay, so that gives us a little bit of a feel for the electrical response of the generator. Now we need to come up with a feel for how does the generator respond on the mechanical side. So if we've got a fossil fuel generator, we've got some fuel coming into the boiler. That boiler produces steam. The steam is controlled by a valve. The steam, as we change the valve position, we change how much steam is inserted into a turbine, sprayed onto the blades of the turbine. As this occurs, we develop a mechanical torque on the blades of the turbine, and we'll call that Tm. At the output of the generator, we've got an electrical torque, Te, that depends upon the power output of the machine and its speed. We can then represent the relationship between the mechanical input torque and the electrical output torque as the mechanical input torque is equal to the moment of inertia of the machine times the angular acceleration plus perhaps some damping torque due, for example, a resistance in the bearings on the turbine and the machine, and also it depends often on some electrical characteristics that are deliberately designed into the generator. J just represents the moment of inertia of the turbine rotor assembly. Alpha here, alpha m, is the angular acceleration of the turbine and the rotor. As I mentioned, a damping torque, and then an equivalent electrical torque here. So this provides us with the simplest generator mechanical block diagram. Okay, recalling from physics that power is equal to torque times the cross product of the angular speed, if we've got a torque that is radially applied, we can say power is equal to torque times speed. So we can then represent Tm here using the equation that we derived before, J alpha m plus Td plus Te sub delta. If we multiply the mechanical torque by the synchronous speed, omega s, then we can define this as being the mechanical power input into our electrical machine, Pm, and then Pm is just equal to the moment of inertia times alpha m omega s, our damping speed, times the angular speed, plus now Pe sub delta, which we derived before. So initially what we'll do is we'll assume that there's no damping on the system, so we'll assume initially that Td is equal to 0. Then we've got a relatively straightforward equation that just says that the net mechanical power in minus the electrical power out is equal to the moment of inertia times the speed times the angular acceleration. So what this means is if at any point in time PM is greater than P electrical, our generator rotor is going to accelerate. Likewise, if PM is less than the electrical output, our generator rotor is going to be decelerating. And the electrical output depends upon the angle delta, which we'll see in a second, depends upon the angular acceleration of the machine. Okay, so here's the equation we had before. If we define the rotor angle as being equal to the synchronous speed, or the omega s, the current speed, I guess I should say, of the machine, times time plus delta, then what we can get is when we differentiate this, we just get the mechanical speed, omega m, which is equal to omega s times the first derivative of the angle delta. And then when we differentiate this again, what we get is delta double dot, which is just the angular acceleration. So then we can represent our equation here saying the mechanical input minus the electrical output is just equal to some value here times the angular acceleration delta double dot. This value here, j omega s, really represents the inertia of the machine at synchronous speed. So what we're going to do is we're going to replace this by a constant, and what we do is we first convert this to per unit by dividing the power on the left and this term here on the right by some MVA rating base. That can either be a rating base for the particular generator or a system rating base. And then what we're going to do is multiply by 2 omega s on the numerator and denominator. And what that gives us is then this equation right here, where we're going to take this value here, j omega s squared divided by 2sb, and we'll define that as h, which is known as the per unit inertia constant, and that has units of seconds associated with it. So this simplifies our equation down that says that mechanical power in minus electrical power out, in this case they're in per unit now, so per unit mechanical power in minus per unit electrical power out times h divided by pi fs, where fs is just our synchronous speed, is equal to the angular acceleration. And then we define this h divided by pi fs as being a constant m, and we get what's known as the generator swing equation, which says per unit mechanical power in minus per unit electrical power out is just equal to m times delta dot, delta double dot. Okay, so as I said, this is known as the generator swing equation. Now we can add some damping back in. In this case, we just add some value d multiplied by the fact that damping is going to be proportional to speed. So we set that proportional to delta double or delta dot. So we get an equation that actually is analogous to a mass suspended by a spring. If you think about a mass suspended by a spring, it's going to sit in some equilibrium point. At that equilibrium point, the force working downward due to gravity is balanced by the force upward because of the spring constant, the spring force. That would correspond here to where PM is equal to P electrical. We're at some steady state operating point and delta stays constant. If you pull the mass down, you're going to stretch the spring out. In that case, the force on the spring is going to be greater than gravity, and the mass, when you do that, is going to accelerate upward and it's going to oscillate around. If there's any damping in the spring due to friction, we know that those oscillations will decay with time, and eventually the mass would come back to some equilibrium point. So here we've got the equation for the mass spring, which is analogous to the equation that we have over here, except now we're, for the power system one, we're talking delta. For the spring, we're talking some position, some vertical position, x with its velocity and its acceleration. Okay, to understand the transient stability problem, usually it's easiest to introduce it by considering what's known as the single machine infinite bus problem. The idea in this problem is we're going to take a single electrical generator, we're going to connect it up through a transmission line with some impedance, JXL, into what's known as an infinite bus. An infinite bus is just set to represent the rest of the electrical system, where we assume that the magnitude and angle of the voltage in the infinite bus stays at some fixed value. So the assumption here is the frequency and voltage magnitude at the infinite bus are constant. A lot of times in per unit, the infinite bus voltage magnitude is set equal to 1 per unit, and its angle is set equal to 0. So we've got single generator connected through a transmission line into an infinite bus that's going to have a fixed voltage magnitude, angle, and hence frequency. Okay, so what we can do then is we can then rewrite this by replacing the generator by its electrical equation. Here we've got a fixed internal voltage magnitude at some angle delta. This represents the transient reactance of the generator. XD prime is the reactance. We convert that to an impedance JXD prime, connect that in series with the transmission line into the infinite bus, and we've got that the electrical power output is equal to the internal voltage magnitude times the magnitude of the infinite bus. In this case, I've neglected it since we're assuming it's 1, divided by the reactance, the Thevenin reactance here, which is just XD prime in series with XD, and then the power transfer through this is just that value times the sine of delta. Okay, so we can then take this equation, which represents our algebraic equation, and substitute it into the swing equation, which we derived earlier, and what we've got then is m delta double dot plus d delta dot is equal to Pm minus P electrical, but P electrical depends upon the internal angle delta. So going back to original formulation of a set of differential algebraic equations here, what we've got is one algebraic equation, and then we've got one second order differential equation, which in the second slide set we'll replace as two first order differential equations. Okay, so the starting point for transient stability analysis is to determine, first of all, what is the equilibrium point? Where would our system come to rest if there were no disturbance on it? And of course, looking at this equation, it's going to come to rest where the mechanical power input is equal to the electrical power output. The electrical power output depends upon the magnitude of the internal angle and the internal voltage and the magnitude of the internal angle delta. So to determine the equilibrium points, we just solve for the points where Pm minus P electrical are equal to 0. If we plot that out between 0 and pi, what we're assuming here is Pm is constant. So Pm can be represented as a horizontal line here shown in red. Then this curve here is just some fixed magnitude that is just a sine function. So it's going to go from 0, reach a maximum, and then go back to 0 when delta is equal to pi. So we solve for the locations where delta is equal to the inverse sine of Pm times the Thevenin impedance here, or Thevenin reactance, divided by EA. And as you can see from the graph, there's actually two equilibrium points, one with a low angle less than pi over 2, and one with a high angle greater than pi over 2. Turns out that our system initially will always be operating at this point here, which turns out to be the stable equilibrium point. Okay, so during the transient stability analysis, what we need to do is actually consider a number of different systems. We're going to start out with what's called the pre-fault system. This is the system before any disturbance is assumed. And the purpose of the pre-fault system is to give us our initial equilibrium point. In large system studies, what we'll find is the power flow actually provides us with the pre-fault initial condition. And then we're going to apply some disturbance to our system. In this example, it's going to be a fault at the terminal of the machine. During the disturbance, the system is perturbed. In essence, you can think of it as being kicked away from its equilibrium point. That's going to cause our dynamics to become active and our internal angle delta to start to respond. And then at some point, we clear the fault on the system. When the fault is cleared, hopefully we return to some new operating point. Okay, so as we, in the third slide set, look at larger systems, we're going to find that the response of the system can be much more complex than this, but they all do tend to fall in the same initial, or the same sort of framework. Power flow gives you a pre-fault condition, you apply some sort of disturbance, and then you look to see where the system settles out. Okay, now there's actually two methods for solving this. One is, since we've got a set of differential equations, the first approach is to use numerical integration. This is by far the most common technique. In numerical integration, what we're going to do is we're going to be integrating a set of first-order differential equations subject to the algebraic constraints. The second approach for solving the transient stability problem is what's known as director energy methods. And in this case, for a two-bus system, we can represent this something known as, in a method known as the equal area criteria, something that we're not going to get into in this slide set here. So in this initial introduction of transient stability, we're just going to look at the numerical integration for solving the transient stability problem. Okay, so let's put it all together here with a single machine infinite bus example. Here, let's assume that we've got our generator represented by the classical model, and it's being supplied through, in this case, we'll set up two parallel transmission lines into an infinite bus where we set the infinite bus voltage as being equal to, again, 1 at an angle 0. We'll assume the lines have impedance JXL1 and JXL2. Here what we'll do is we'll apply a fault right at the terminal of the bottom line here. So the fault will be applied, and then we will clear the fault by opening the two circuit breakers for the transmission line on the bottom here. So pre-fault is this, everything in service. The faulted system is going to have this point here shorted to ground through what we'll assume is a balanced three-phase fault, and then we'll clear that fault by opening this transmission line. So in our post-fault system, we'll have the generator again connected to the infinite bus, but through one less transmission line. So the net impedance here joining the generator to the infinite bus will be reduced in the post-fault situation. Okay, so we can simplify our pre-fault system by combining the impedance of the two transmission lines in parallel with the internal impedance on our generator and just define that as JX Thevenin. We've got our voltage magnitude EA at some value delta. Again, we set up the equation here, the P electrical equation, which is just a constant times the sinusoidal, and we're looking for this equilibrium point here. In this case, it's the delta that satisfies this equation right here. During the fault then, what we'll have is this point of the system, we'll assume it's right on the line side of the circuit breaker, so there's essentially no impedance between this point here to the left of the breaker and the fault itself. So what this looks like is during the fault, it looks like our generator is connected to ground through its internal impedance. So if you look at this, during the fault, no power can be transferred from the generator to the system. Okay, so that means that since we've still got a PM coming in, we can't get any electrical power out. Our generator is going to start to accelerate during the fault. And then for the post-fault condition, what we'll have is the generator here through its internal impedance, the internal voltage through the impedance. This line has now been cleared by the circuit breakers and it remains out for the remainder of the study. And then we've just got a single transmission line here. So the equivalent system after the fault can be represented by JXD prime in series with JXL. And again, we've got a voltage here. The assumption on the classical model is the magnitude here of the voltage, EA, stays constant, and delta is going to be free to vary. So if we want to represent that graphically, we've got now three curves representing P electrical before the fault, P electrical during the fault, in which P electrical is equal to 0, and then we've got our post-fault curve here, which is reduced in magnitude, since now we're supplying our generator into the infinite bus through a higher net impedance. Then during the disturbance, the form of PE change, or PE sub delta, changes, and that's going to alter our power system dynamics, going from our equilibrium point to a point where we can't get any electrical power out, causing our internal angle to start to increase. And then hopefully when we get to the post-fault system, we will not have increased too much that we'll be able to come back to a new post-fault equilibrium point.